Okay, we're going to continue our waves unit. We're going to start out by talking about light and sound. We'll make one note. Light can travel through a vacuum. We'll talk about that more in a moment. All right. Now, the color of light depends on the frequency and the wavelength. Okay, if I think of the color of the rainbow, red, orange, yellow, green, blue, indigo, violet. Red is long wavelength, low frequency, and violet is short wavelength and high frequency. The brightness is determined by the amplitude. So a high amplitude light wave is going to be bright. And I want to make a note of this too, that the velocity of light, we use the letter c for it because it's a constant, is 3 times 10 to the 8 meters per second, at least in a vacuum. For sound, sound can't travel through a vacuum. It requires a material medium, for instance, air. Okay, it's the air molecules bouncing off each other. Now, it's not just air. It could travel through water. It can travel through a solid. Actually, in a solid, it's going to travel fast because the molecules are very close together. Okay, but it needs those molecules, so it can't travel through a vacuum where there are no molecules. The frequency and wavelength determine the pitch. So a high pitch is high frequency. Which is going to be a short wavelength. And that's why an instrument like a flute is high pitch because it's short, has short wavelengths, as opposed to a longer one like a trombone has a lower pitch. The amplitude is the volume of the sound. So loud sounds have high amplitude. And the velocity for sound is about, now it varies with temperature and pressure, but it's going to be about 340 meters per second at STP. So it's much slower than light. That's why when you see a lightning storm, you see the flash long before you hear the sound, because the light gets there almost instantaneously, 3 times 10 to the 8. It's very, very fast, and it takes a little longer for the sound to get there. It's about 5 seconds per mile. So if you count 10 seconds between the flash and the thunder, that means it's about 2 miles away. Now, electromagnetic radiation, use electric and magnetic fields is their medium. Okay. They can travel through a vacuum then, because electric and magnetic fields can be in a vacuum, and their speed is 3 times 10 to the 8th. So we call 3 times 10 to the 8th the speed of light, but it's actually the speed of any type of electromagnetic radiation. Now, the different types just have different frequencies. I'm going to make a little chart. Okay. And over here we're going to put low frequency, which is long wavelength. Over here we're going to put high frequency, which is short wavelength. Now right in the middle is visible light. And it's a very narrow band, just a very few frequencies. And the lowest frequency over here would be red, and the highest frequency over here would be violet, and all the colors would be in between there. Now just below red, we have a wave whose name means below red. It's infrared. Frequencies just below that are microwaves. And then below that are radio. So radio waves have the longest wavelength and the lowest frequency. Now right above light, above violet, we have one that means above violet. It's ultraviolet, UV. Higher than that are X-rays. And the highest frequencies are gamma rays. Polarization. Okay, so polarization, the definition of it is one direction of vibration for a transverse wave. Because a transverse wave, it has to vibrate perpendicular. So if I imagine a wave going to the right, well, up and down is perpendicular to that, into and out of the page is perpendicular to that, and then any angle between there can be perpendicular to that. So there's lots of different possibilities for how the transverse wave is vibrating. If we pick out one, that's called polarizing it. So here is a light wave that's a mixture of waves that are vibrating up and down, waves that are vibrating into and out of the page, and then this is a vertical filter. It's only allowing through waves that are vertically polarized, vibrating vertically. Horizontal filter is going to only allow ones that are going horizontally. Now, an example of where this is used in real life is in polarized sunglasses. Okay, so what you have is sunlight. So we'll put the sun over here. So sunlight comes down, and it has all polarizations all mixed together. So some of them are vibrating perpendicular, some are vibrating horizontally, and some are vibrating, at some angle between those. But then when it hits a non-metallic surface, like glass or water, it's going to come out horizontally polarized. we call that reflection off the ground glare. So because this is a horizontal surface, when it reflects off, it's going to be horizontally polarized. Then the sunglasses are vertically polarized, or they're a vertical filter. So they're going to block that horizontally polarized glare.